Hello everyone. Today we are gonna talk about GCD and LCM. So first of all, what is GCD and LCM? The GCD is the greatest common divisor, and LCM is the least common multiples. So for example, GCD 2 and 8 equals to 2 because 2 divides 8 and 2 divides 2. So that's the greatest common divisor of 2 and 8. However, GCD 3 and 8 that equals to 1 because the greatest common divisor of 8 does not contain the greatest common divisor of 3, which is 3. So these two numbers are relatively prime. Now let's look at LCM. So LCM 2 and 8 that equals to 8 because 2 divides 8 and 8 divides 8. 8 is the least common multiples of 2 and 8. However, LCM 3 and 8 that equals to 24 because 24 is the least common multiples of 3 and 8. Maybe we all learn this stuff, but now let's look at some properties of GCD and LCM. For prepositions of GCD and LCM, we have first, if GCD AB equals to D, then there exist integers A1, B1 such that A1 times D equals A and B1 times D equals B, where GCD A1, B1 equals to 1. The second one says that if A equals to QB plus R, then GCD AB equals to GCD BR. So for these two prepositions, the proving is kind of intricate, so I'm not going to introduce that during the video, but if you're interested, you can contact me through my email. But we can see some examples through this preposition. So let's take, for the first preposition, let's take A equals to 6 and B equals to 21. And obviously GCD 6, 21 equals to 3. And 6 equals to 3 times 2 and 21 equals to 3 times 7. And that's B1. And this is B1. And GCD 2, 7 equals to 1. As the first preposition said. For the second one, let's take A equals to 100 and B equals to 30. And 100 is 30 times 3 plus 10. So the preposition said GCD 130 equals to GCD 3010. So 130 the greatest common divisor of 130 is 10, and the greatest common divisor of 30 and 10 is also 10. And that proves the preposition. Besides the prepositions, there are also some important theorems that we must know. The first one is called the Euclidean algorithm. In this theorem, it says that A bigger than B be integers, be positive integers. Then you can apply the division algorithm such that let A be the form of B times Q1 plus R1. Then let's take B and R1 and keep doing that. And B equals R1 times Q2 plus R2. Let's take R1 and R2. R1 equals to R2 times Q3 plus R3 until that RK minus 1 equals to RK times QK plus 1 plus RK plus 1. As we can see, if A is divided by B and there's some numbers left, B must be bigger than R1. Similarly, R1 is bigger than R2 and R2 is bigger than R3. So, as these are non-negative integers, there must be some k such that this number, rk plus 1, equals to 0. At this step, we show that GCD AB equals to RK. Why is that? Because as we can see that GCD AB is equal to GCD BR1. This is stated as the preposition set, and that is also equals to GCD R1, R2, and so on until GCD RK plus 1. Since RK plus 1 is 0, so GCD RK, that's just RK. So as we keep doing that until RK plus 1 is 0, then we find the greatest common divisor of A and B. You can see some examples. Let's take random numbers. So like, for example, that A equals to 3030 and B equals to 96. So let's follow the steps of Euclidean algorithm. So first, 3030 equals to 96 times 31 plus 54. Then we take 96 and 54 and keep doing it. 96 equal to 54 times 1 plus 42, and let's take 54 and 42. 54 equals to 42 times 1 plus 12, and 42 equals to 12 times 3 plus 6, and 12 equals to 6 times 3 plus 0. Then the GCD of 3030 and 96 equals to 6 as the zero set. As you can see, this is much easier to just think what is the greatest common divisor of 3030 and 96. We can just do some calculations and to find it out. Now let's see the next theorem. It is called the Bizar's identity. This theorem said for any positive integers A and B, their integers x and y such that ax plus by equals to GCD of A and B. So, for example, if you have GCD 3 and 8, z equals to 1, and the theorem said there must exist x and y such that 3x plus 8y equals to 1. You can figure out that if y equals to 2, that's 16, and x equals to -5, z equals to -15, and that's 1. So the theorem proves that. And there are some important corollaries. The first one states that if A divides BC and GCD of A and B equals to 1, then A divides C. Why is that? So if C does not equals to 0, then as the results identity says that AX plus BY equals to 1. And if we times both sides by C, then ACX plus BCY equals to C. And as A divides BC, this is, so A divides BCY. A is also divides ACX because A divides A, thus A must divide A must divide C. For the next one, we have that GCD of A and B equals to 1. If A divides C and B divides C, then AB divides C. To prove this, let's make C equals to 81, then A divides AD1, and B divides AD1. However, since GCD A and B equals to 1, so B must not divide A, so B divides D1. So let's make D1 equals to B times D2. Since C equals to AD1, then that is also equals to A times B times D2. Therefore, AB divides A times B times D2.